So state two factors which determine the speed at which a vehicle negotiates a banked road safely. Okay, so we have to state two factors which determine the speed at which a vehicle negotiates a banked road safely. Yes. Yes, one. Let me pick your views. One. Two factors which determine the speed at which a vehicle negotiates a banked road safely. One. Anybody? What will be the first or one of the factors which determine the speed for which determine the speed a vehicle negotiates a bank safely? Don't forget when we went through the banked road, we saw that its speed or square of its speed is equal to the radius times the tangent. Okay, this is when the road or the vehicle only does not depend on friction. And so v squared, v is equal to square root of rg times tan theta. So v is the speed. So which factors here, okay, which factors here determines the safety of car negotiating a banked road? Yes, Ayo, give me one. Jojo, give me one of the factors.
Yes, one of the factors includes the what angle.
So the banking angle. Okay. So
yes,
it depends on the banking angle. And Nathaniel, so the banking angle theta here. Yes, Nathaniel.
Yeah, please. Velocity of the body.
Look at the question. The question actually says that state two factors which determine the speed. Okay, yes, at which a vehicle negotiates a bend. So factors which will determine the speed or what you also term as the velocity. Okay. What other factors will determine the speed here? Apart from Elsie, from the equation, what other factors apart from the angle will determine the speed or the velocity? Oh, let's not waste time. The radius of the road. Don't forget, we had that v is directly proportional to square root of the radius. The larger the radius, the larger will be the speed or the velocity. Then v is also directly proportional to square root of tangent of the banking angle theta. So it means that the larger the angle of bend or bending or banking, the larger will be the speed or the velocity. That is why for riders, motor riders, if they need to negotiate a bend with that top speed, they need to bend the motor, okay, even to the extent that the whole body is almost touching the ground to make that bend. As for velocity, as for gravity, it's a constant, so it has nothing to do with it. Nathaniel.
Please, can I say coefficient of friction?
Yes, it's also a factor. Yes, you can also say that in the situation where we are looking at both banking angle and friction. Okay. Or you can simply say friction instead of coefficients. Okay. The other question is that a 500 gram is a calculation question. So please get ready to write it for me. A 500 gram sphere. A 500 gram sphere is hung from an inextensible string. A 500 gram sphere is hung from an inextensible string. Inextensible string, which is 1.2 meter long. Which is 1.2 meter long and swung around. We are told that its length is 1.25 meter long and swung around to form a conical pendulum. It is swung around to form a conical pendulum. The sphere moves in a circular path of radius. The sphere moves in a circular path of radius 0.75. 0.75 meter. Find the angle of inclination. We are to find the angle of inclination. Then 2, the tension in the string. The tension in the string. Take gravity to be equal to 10 meter per second squared. So a 500 gram sphere is hung from a string, from an inextensible string which cannot be extended or stretched. 1.2 meter long and swung around. So assuming this is the support, let me use straight lines. But there's a vertical, and then this is the sphere. The sphere is here. We are told that it has a mass of 500 grams. .500 grams. The length of the string, we are told, is 1.25 meter. It swung around to form a conical pendulum. So for a conical pendulum, there is angle of inclination theta. So the string is actually swung around and the base, the string, we are told that the string, what is the question? Okay. To form a conical pendulum, the sphere moves in a circular path. So the sphere moves in a circular path such that it describes a conical pendulum. Okay. The radius of the circle described, we are told, as 0.75. So that's the information. Now we are required to find the angle of inclination and then the tension in the string. So 3 minutes, let's see what you can produce out of this question. 3 minutes, it's 6:16. So work around it. Let's see what you can be able to produce. I'll come your way right after the 3 minutes. So okay, since it's a 2-in-1 question, let me give you 5 minutes. 5 minutes. So 6:21, I'm coming your way. We have 3 minutes more. Your time is up. So let's see. Let's see. So we are going through the question, and then you actually mark yourselves for me. So first we have to find the angle of inclination. You see, relations about conical pendulum, we have its speed or square of its speed being equal to RG times tan theta. We also realize that for a conical pendulum, its period of oscillation is equal to square root of L cos theta divided by G. Meaning that if we have the period, we could have used this to find the angle, okay, the angle of inclination. Here, we should have speed or velocity. The radius, we have it, G, to determine the angle tan theta, because if we use the first one, tan theta is equal to V squared over RG. Okay, we don't have the speed. So how do we find the angle of inclination, class? Let me have your take.
Please, for mine, I use the equation R is equal to L sine theta.
Exactly. That is the obvious way to look at it. Okay. So if you take sine theta, sine of the angle of inclination, this is equal to sine theta is equal to the radius over the length. And we have all that. We have the radius, we have the length. So we can use this to find theta. So this is how we must go about it. The radius is 0.75 divided by the length 1.25. Theta therefore is equal to the sine inverse of this ratio, 0.75 on 1.25. And what's the answer? What's the value of theta?
36.9.
So approximately 37.
36. Yes, please.
Approximately 37. Please show by hands those of you who got the first part correct. If you got the first part correct, let me see you and clap for you. Show by hands. So I have, okay. Frida, okay. More hands, so. Okay. 7 of you. All right. 8 of you. Okay. Good work. 9. Thank you. Then the second part. So please, if you couldn't figure out how to solve it, this is the way out. That is why yesterday I gave you all the required equations. The next question is the tension. We have to determine the tension in the string. Tension, if you recall, we equated T cos theta balanced the weight mg. Mamiya, your hand is still up. And T sine theta also balanced the centripetal force, mv squared on r. Okay, we don't have v. We have the mass. So obviously, we can use this to find, because when we use the second equation, because we don't have v, we don't have t, it will be cumbersome. So using the first equation, T cos of 37 is equal to the mass, which is 500 gram, which is 0.5 kilogram, times we are asked to use acceleration value of 10. So T therefore would be equal to 5 divided by cos of 37 degree, which is, what is 5 divided by cos 37 degree? Yes. Those of you who calculated for it, quickly do that for me.
6.260.
6.260 Newton. Okay. Please, if any of you use a different approach in solving it, you can also let me know. All right. So, Amia.
Please, for mine, I tried to find V by using by first finding the period, and I used the period to find the angular velocity, and I used that to find the speed, and I used that to find.
So you determine the period.
Yes, please.
And because you have the period, V is equal to omega R, which is 2 pi over T, the period, times radius. Okay. So when you determine the period using this, you have 1.25 times cos of 37 over 10, and you have the period. So once you have the period, you can find V. Then you substitute V into this. Yes, that's true. Maria's method is quite long, but it will also give you the same value. Did you get the same answer?
If I didn't complete it.
Okay. So you can complete it later and then compare. Okay. All right.
Yes, please.
So class, this is the solution. Okay, to the question. I'll look for another one, send it to you. Please, if you have any question, quickly bring it up for explanation. Is there any question? All right, then let's look at the final part of circular motion. Here, uniform circular motion. Uniform circular motion. The horizontal, the conical pendulum whirling an object at an angle 0 to the ground. Okay, these are all horizontal circular motion. So objects tied to the ground and whirled. I mean this. If you tie a stone to a thread, okay, and then you whirl it.
You swirl it.
You
Okay,
swirl. You swirl or you whirl. Okay. Whether you swirl or you whirl, it must actually rotate. So this is the length of the string, which is also equal to the radius. Okay. This is a form of horizontal circular motion. Then the conical pendulum, as we just saw, is also another form of horizontal circular motion. Okay. Now let's look at vertical circular motion or vertical oscillation, vertical circular motion. In vertical circular motion, the object, okay, is whirled vertically. An example, an application of this is the roller coaster. The roller coaster. The roller coaster moves along the vertical plane. So here, the motion of the object, goes or is whirled along the vertical plane. So the direction of motion of the object is along the vertical plane. Okay, and this one, the object moves along the horizontal plane. Okay, an application of this is a roller coaster. Please, if you have an idea of other examples, you can also share with me. Apart from the roller coaster, which gadget also moves along the vertical plane? I know the centrifuge is force within the, I think, horizontal circular motion. The centrifuge is an example of this, but the roller coaster is a vertical one. If you have any idea of a machine which, I mean, rotates along the vertical plane, you can share with us. Okay, I'll later Google for more examples and then share with you. Okay, so in vertical circular motion, the object moves within the vertical plane with that constant velocity. So let's assume the directional, okay, let me indicate the axis. So the object, we are picturing the object to be moving in that anti-clockwise circular motion or direction. So at one point, the object is here. The object is also here. The object can be here. The object can also be here. Now, when the object is here, what happens? B, C, and D. Vertical circular motion. Now, let's pick it from, I'm giving a simple explanation, then we'll look at what happens at any other angle theta. If the object is below or down, this is down at D and up, A and B, because the level is the same, whatever happens here is equal to what happens here. Now, when the object is down, what will be the direction of the object? The direction of the weight of the object. Yes, anybody? When the object is at the point D, down, what is the direction of its weight? Oh, a quick contribution. Jojo and Co. What will be the direction of the object's weight? Hey, Mami Yamu. Bernard Baden, Chris, Elsie.
Please say weight to be down.
So weight is always in line with gravity. Okay. So it would be in this direction, downwards direction. So we have mg. The tension within the string is always directed to where the support is, and the support is the center. So tension would act here. When the object is at the top, at the upper part of the circle, yes, we have its weight. There's the object. Its weight will still be acting downward. It will follow gravity. Then the tension is always directed to a point of support T. Okay. Now, at below or down the curve or the circular path, what will be the net force acting on the body? When the body is at below the curve, what do you think will be the expression for the net force acting on the body? Yes, anybody? The expression for the net force acting on the body. Yes, Elizabeth.
Please, I think it will be T plus mg.
Is that T
Plus mg.
plus mg? Can you
Yes,
explain?
please.
Can you explain?
Please. Like the sum of the upward and like the downward forces down there, I think we go to the weight.
So you think the net force must be T plus mg?
Yes, please.
Okay, more views. That is Elizabeth's view. More view. What do you think below will be the expression down? I mean down will be the expression for the net force. Yes. Yeah, you
I think that the net force may be 0.
What's your reason?
Because the tension and then the mass times gravity won't be the same.
You cannot assume that they are the same. Okay. Now, let me also come in. When it's below and mg is greater than the tension, what do you think will happen? If mg is greater than the tension in the string, what will happen?
The string will stay down. So the net force will be mg minus tension.
And so what practically, if this happens, what will happen to the object? The object
will be heavier.
Pardon?
The object will be heavier.
It means the object is heavier than the tension, and the object will tear off because the weight is greater than the tension in the string. Okay, so if the object does not drop or tear off, what it means is that the net force must be equal to either T must be greater than mg or equal to. So if the object does not drop or fall off, then the tension in the string is either greater than the weight or both are equal. So in this case, the net force must be T minus mg. It cannot be mg minus t, because when this happens, the object cannot stay in the circular path. It must drop. Class, are you okay?
Yes, please.
Then,
Mr. Edia,
hello.
please can you come again?
Okay, you see, we are looking for the net force acting on the mass below the curve down here. Since we have two forces in opposite directions, okay, it means that the difference between the forces must give you the net force acting on the objects down the circular path. But if the object could still whirl along the vertical plane, then it means that the tension within the string must be greater than the weight, because if it's the other way around, you will drop. It is equal as tying an object to a string. If the weight of the object, let me even use you, Leslie. If you are suspended on a string, okay, and your weight is greater than the tension in the string, what do you think will happen to you, Leslie? In a situation like that, what do you think will happen to you? You will fall, because you will tear it off. It means that the tension wouldn't be enough to support your weight. Leslie, are you okay?
Yes, please.
So it means that if the object could still stay within the circular path, then either T is greater than mg or both are equal. So the net force in this case must be the tension minus the weight of the object. Okay. Now it means that the net force always follows the direction of the larger force. Net forces always follow the direction of the larger force. Let's write that down. Net force or forces always follows the direction of the larger force. Of the larger force. So once the tension in the string is greater than the weight, the net force will act in the direction of this. So T minus mg must be equal to, and since this is circular motion and a certain net force is directed towards the center of the circle, we equate the net force to the centripetal force, mv squared over r, or m omega squared times r. Okay, so we have T is equal to mg plus mv squared over r. When we factorize out m, we have the expression v squared over r plus g all times m when we pull out or factorize out m. So below the circular part, this is the expression for the tension in the string. The tension T in the string. V squared over r is the centripetal acceleration. So we can also say that this is equal to AC plus G times M, since AC is equal to V squared over R. Okay. So below, this is the expression for the tension within the string. Let's also consider above the circular part. What will be the net force? Yes. So above or up the circle at the point B, what will be the expression for the net force? Yes. Somebody should help me. Leslie, you help me. When the object is above here, what will be the expression for the net force?
Please, I think it will be T plus mg.
Exactly, because, Leslie, because, what is your reason? Why are you saying this? Yes.
Mr. Please, maybe T is equal to mg.
Oh, what is your reason for saying that the net force will be T plus mg? That's my question. Your vectors is has become rusty. Yes. What is your reason? Yes, class. Anybody?
Miss
Mm-hmm.
Mr. Is it because they are moving in the same direction?
Exactly. When two vectors are along the same direction, okay, the resultant is equal to the summation of all of them. When two people, two of you are pushing a car, the combined force acting on the car is the summation of your forces, isn't it? So apply your vectors well, because I taught you. So in this case, the net force is equal to T plus mg. Now, what is the direction of the net force? What is the direction of the net force in this case? Class, what is the direction of the net force? Eva, Mamiya, Ayo, and Co. Speak. Isaac.
It says toward the center.
Towards the center, because the two vectors or forces are acting. So because the direction of the net force is towards the center, we equate it to the centripetal force. mv squared over r is equal to T plus mg. Let's make T the subject. T therefore would be mv squared over r minus mg. M out, we have v squared over r minus g. In other words, this is M out AC minus G. So this is the expression for the tension. Now we have two expressions, T, the first one, and then this second one, which is AC minus G times M, equation 2. Now, look at equation 1 and equation 2. Which one would give us the maximum tension and which one would give us the minimum tension? Equation 1 and equation 2. Which one would give us the maximum tension in the spring and then the minimum tension in the spring? Yes. Yes. Yes, Mamiya.
Equation 1.
Equation 1 would give us, Mamiya, equation 1 would give us the what?
The highest tension.
So maximum tension. And equation 2 will give us minimum tension within a spring. This is because, you see, these two are adding up. They are adding up. And here one is subtracted. So this one, equation 1 will be greater, whereas equation 2 will be lesser. So when a body is in vertical oscillation, okay, we have maximum tension down the curve. Maximum tension occurs down, whereas minimum tension occurs up the circle. So T maximum would occur below, whereas T minimum would occur above. Please take note of this very important concepts. Okay. Is there any question? Because I want to move to when it is at any angle theta, what happens? So when it is at any angle theta, what will happen? So point E so A, B, C, D. Now let's consider at any angle theta. Meaning when the body is here. And it makes any angle theta with either the horizontal or the vertical. What will happen? If the object is at this point, its weight will act here. The weight will always follow the line of gravity. So mg of the object. If we extend this line, if we extend this line, this is the rope. So we have this as the tension in the rope. T. But when we extend this, hang on, let me indicate the angle well. Okay, so the angle is 2. The reference point is at D. So angle is at this point theta. Obviously, this will also be 90 minus theta. So when this angle is theta, this will also be theta. Do you agree with me? Do you agree with me that if this is theta, this will also be theta? If you don't see it from that angle, another way out is this. If we extend the weight vector up, we will realize that this angle would alternate with this angle. So if this is theta, this will also be theta. And by vertically opposite angles, this will also be theta. Okay. All right. Now, if this is theta, then we have the weight vector mg tilted at an angle theta here. And in physics, whenever a vector quantity tilts at an angle, we resolve it into components. We need this component. We just need this component. Okay, the adjacent to the angle. And this will obviously be mg cos theta. So this component is mg cos theta. Here, we don't need the vertical component, but obviously that will also be mg sin theta. Please, are we okay with this component of the weight mg cos theta? Class, are we? Hey, let me have your view. So
Yes.
so that it wouldn't be an imposition on you. All right. So if this is mg cos theta and this is the object in circular motion, it is moving in that anti-clockwise direction. When it is here, we have two forces acting on the body. We have the tension acting here, and the component of its weight, mg cos theta, acting here. What will be the net force acting on the body at this position? Yes, class, what will be the net force? The net force. Mamiya, what will be the net force acting on the body if we have this downward component of force and then the tension in the spring? What will be the net force?
T minus mg cos theta.
Mamiya, why not the other way around?
Because if mg cos theta is going downwards, then it has to be negative because the y-axis going down the y-axis is negative.
So just as it's the same reason that I said, if mg cos theta is greater than t, the objects cannot be in that circular motion, meaning the weight, this component is greater than the tension, and so the string must stir up. Is that okay? So it must be t minus mg cos theta. T must be greater than mg cos theta. Okay. Now, the net force always follows the direction of the larger force. The net force will always follow the direction of the larger force. So, because the larger force is acting towards the center O, we equate it to the centripetal force, which gives the object within the circular path. So, mv squared over r is equal to t minus mg cos theta. Please, let's make help me make theta the subject. Help me make theta the subject. T the subject. Ayo, do that for me. Calculate and then give me feedback. You are making T the subject.
Please say T. You said T, right?
Yes, the tension.
T will be equal to mv squared over r plus mg cos theta.
So mv squared over r plus mg cos theta. So this is the general expression for the tension at any angle theta. At any angle. And note that when the body moves from D to A, what is the angle covered? When it moves from D to A, what is the angle covered by the body? At A, what is theta? At A, theta will be equal to what?
90 degrees.
90. So at A, it means that the body has moved from D to A. So if theta is 90, then look at the expression for the tension. Tension will be equal to, cos 90 is 0. So the tension is equal to the centripetal force mv squared over r. when the body moves to B, so at B, what's the angle? When it moves above the circular path, what is the angle theta? At B, yes. Yes, quick one. At B, what is the angle?
180.
180 degrees. So theta is 180 degrees at B. Okay. And what would be the expression for the tension? What would be T when theta is 180? Put your values in and then share it with me. Substitute 180 for theta and then give me the expression for the tension. Let's hurry up. Yes. What is T when theta is 180 or when the body is above the circular path, when it is up here? Mamia. Ayo.
Yes.
Yes.
Yes, Frida.
Yes, Frida.
MV square over R minus MG.
So we have, I'm coming in. I'm coming. I'm just. Okay, so when we substitute that in, we have MV squared over R plus MG cos of 180 degrees. The network has started to misbehave. And cos 180 is -1. So we have T is equal to MV squared over R minus MG. This is still the same as M out V squared over R minus G. And it confirms whatever we derived earlier, that above the circle we have minimum tension, okay, within the string. So this also confirms exactly what we've done earlier, that minimum tension within the string always acts above. Then when at C, what is the tension? At C, theta is 270. Okay, so when we substitute it into this equation, we have MV squared over R plus MG cos 270 degree. And class, what is cos of 270 degree? What is cos 270?
Please, 0.
0. So it means that at C, the tension is still MV squared over R. Exactly as I said earlier, that at A and C, because they are at the same level, the tensions there are the same. Okay, at A we had FV squared over R. At C we are getting the same value, FV squared over R. Then finally at D, what is the tension, please? And at D, theta will be equal to what? At D, what's the value of theta?
360.
That's 360. So substitute 364. 360 for theta, and then give me the value of the tension. Yes, do it and then report to me. When theta is 360 degrees, what is the tension? Please get involved so we do this quickly. We are almost ending, so. The network, Elizabeth.
Please, I got cos 360 to be 1, so then the T was equal to MV squared over R plus MG.
So MV squared over R plus MG. Hey, the network will not allow me to write. So we also realize that below we have maximum tension acting here. So this is a general formula we caters for any position as the body oscillates vertically. Okay. Earlier we only analyzed for when the object is at above and below, but this expression is giving us any general angle theta. Okay, and the expression of the tension within the string. So sometimes you'll be asked to calculate for the minimum tension and the maximum tension within the string. And this is what you must apply to do those calculations. Are we okay? Class,
Yes.
are we okay? All right.
Yes, sir.
All right. I think the network has started to misbehave. So what I'll do is that we are left with just a small aspect, and that is how to calculate potential energy and the kinetic energy when the body is in vertical oscillation like this. I wish the network would favor us so we can do it, but from the look of things, I think it will not allow us. It keeps on breaking. Let me just try. If it works, fine. If it doesn't, then we treat that quickly, then next week, and then start with simple harmonic motion. So when the body is executing circular motion, vertical oscillation for that matter, there's a reference. And the object moves from the reference point, this point A, and come to any position here, making a certain angle theta. So the angle described here is theta. This is the length. One is the center. L is the length of the string. Okay, so is this length too. Now, if you want to calculate the potential energy of the body at this point B. We want to determine the potential energy. As for kinetic energy, KE is always half the mass times the square of the velocity. But we know PE, this is gravitational potential energy, to be equal to mass times gravity times the height. What is the height? Please open your eyes and watch this. When the body moves from A to B, the vertical height covered in its movement is this distance. So this distance from here to here, which is also the same as this height, is the height covered. Okay, so if we are calculating for the potential energy of the body at this position B, it is equal to the mass times gravity times this vertical height at B. Okay, at B. Now, how do we determine H in order to calculate for this potential energy? Let's assume that this is X. This distance from the center to this point is X. Okay, let's call this point maybe C. So the center OC is equal to X. This I'm coming. I want to do something about. Okay, so hold on a second for me. Okay. So OCX. Okay, but the whole of OA, oh shit. This will not write too. Class, I'm coming. You would rejoin, okay? You will rejoin. Let me see if this would actually work out. Hello, are you there?
Yes, please.
I'm coming. I want you to see if I can change the network setting. It's becoming difficult now. Hello. Hello, Chris.